Hello and welcome. Today we're just going to be doing a couple examples of Riemann sums. All right, so I just want to recap that the idea we're talking about here is that f of x equals y. We're going to say it's continuous on some interval. Okay, and that means it's integrable. So the integral means that basically this symbol, I can express it or find a way to compute it by taking the limit as n gets very, very large of some summation of f of x of I star times delta x of I as I goes from 1 to n, where the xi star are within this x of I to x of I plus 1 subintervals of partitions x of 0, x1, x2, all the way to xn, where that is x of a, and that can be b there, and at every other point, these are points in between that form a way of breaking up the interval. All right. Okay, so with this defined, let's actually just do some examples. Let's do some really straightforward examples. I want to talk about one that we should be able to do geometrically. I want to integrate the function f of x. So let's do an example. F of x is equal to x, and we're going to do it on the interval 0 to 1. Right, so this should be fairly straightforward to calculate. In fact, we should be able to, if I just draw a picture of it, there's 0, there's 1, and there's 1 for the y-axis. And we know it's a straight line going up like that. Okay, so the area under this curve, well, we should be able to get that with just basic geometry. So the area should be, of course, just 1/2 times the base times the height, which in this case is going to be 1/2 times 1 times 1 is equal to 1/2. All right, we know that's true. Let's now go through and do the much more complicated method of using the Riemann sum to do it. All right, so what I'm going to do is I'm going to just use the right endpoint rule. On even spaced partition on partitions. So in this case, we're going to take n. That's going to be our control parameter of how many intervals we're taking. And we know that our xi is, of course, going to be b minus a over n times I, where I is going to go from 0 all the way up to n, and that gives us the n plus 1 partitions. Okay, and we're going to take xi star to be equal to x of I plus 1 in this case. Actually, pardon me. It'll just be x of I. It'll be very simple. And here we're going to take I equals 1 to all the way to n. Right. So this way we only have n of those ones right there. Okay. In order to compute this, though, I'm going to actually recall that we have a special sum formula, and that is the sum of consecutive integers, I from 1 up to n, has a special formula. It's going to be n times n plus 1 all over 2. All right, so anytime I see one of these, I can put this much simpler expression that doesn't involve I at all in its place. Okay, all right, so I'm going to go to the next page now. And now let's see if we can construct this sum. All right, to construct this sum, we're going to, of course, know that f of x is just equal to x. And my x of I, of course, are going to be, so b minus a, we know that's going to be 1 over n times I. Okay. And then what we're going to do then is we're going to then say my delta xi, of course, are going to be 1 over n. Okay, good. So we know the formula goes like this. I equals 1 to n of f of xi. Sorry, these are x of I stars there. Well, oh, sorry, undo. That's x of I, and then the x of I star, of course, is going to be the same thing. That's what we should say more carefully. Times, and now we're going to put that delta x there. And I can rewrite this to be, now I just drop into place all the components we need. So f of x is just equal to x. So anytime I plug in a value down here, I actually just have to plug in I over n, because that's what x of I is, x of I star is. And now we're going to times it by delta x, which is 1 over n. Okay, great. All right, so we know that this is this way. Now we see that that's actually not a function of I, that factor there. So actually this should be able to move out front the 1 over n squared. And I do that, of course, to isolate this component right here. And of course we know that that's equal to, that is the sum of consecutive integers. Which of course is going to be n over n plus 1 all over 2. All right, so what this is, of course, is that approximate Riemann sum. Okay, and now, of course, we need to take the limit to get the Riemann sum. So we take the limit, n goes to infinity, of n times n plus 1 all over n squared times 2. All right, so I need to do a little bit of simplification here. I think we see what the value of this limit is going to be. We have an n squared plus n. I just distribute in the n to both of those inner terms there. And now I have an n squared times 2. All right, so we see up here we have, those are the leading orders, or the leading powers. All right, and so we know those are going to dominate, and it's the coefficients out front of those, 1 on the top and 2 on the bottom, and everything else is going to be irrelevant in size, and that is going to give us this limit, which of course is exactly what we found earlier from geometry. All right, so the Riemann sum works. It actually gives us the value we expect. All right, so now I want to keep going now and do one more example to wrap up this video. So I'm going to go to the next page, and now we're going to compute the integral from 0 to 1 of x cubed minus x dx. Right, we can interpret this as the area under the curve of this graph over that interval. It probably is worth our time to actually ask ourselves, what does the graph of this look like? Well, let's see what it looks like. I can see that there's a common factor of x in both of those terms. I could factor it out, and I get this. And I see that this, of course, is a difference of squares, so I can keep factoring it. Right, so the interval we're looking over, of course, is going to be 0 to 1. And the other thing I note, that x on this interval implies that f of x is greater than or equal to 0. All right. Oh, no, I'm sorry. Undo that. Is less than or equal to 0 over the whole interval. In fact, if we were to graph it, what we're going to find is, of course, we know the zeros. The zeros, of course, are going to be 0, -1, and 1. So if I were to put a little blue line through there, and now what I'm going to get is, oops, undo on that. I get a curve that looks like this. So what we're trying to find then, of course, is the area under the curve right there. All right, so we haven't talked about this yet, but what I'm going to note about this is that the area under the curve is actually below the x-axis. What I'll say immediately about this is actually we're gonna calculate a negative area. All right, and that's somewhat of a strange concept that an area can be negative, but it turns out that this is totally okay. We'll just allow anytime there's an area below a curve, below the x-axis, that we're going to interpret that as a negative area. If you don't like that it's a negative number, of course, all you have to do is just flip the sign. We're going to talk more about the significance of that negative area, why we have negative areas, and why they can be useful concepts in later videos. But for now, let's just actually see that this will, in fact, calculate to a negative area. So, another important facts. Here's some important facts just to keep in mind. Again, we know that this sum, I'm going to just write that one down again. And also, there's another formula for this one, which is quite similar. It's actually going to be the same form as the last one. Oh, sorry, my bad. I'm getting ahead of myself. The sum of cubes, the formula for the sum of cubes is similar to the sum of consecutive integers, but we just square the result. All right, so let's now use these important facts to compute this integral. Again, I'll use the right endpoint rule. Again, the theorem says that we can use any rule we like, and I just find this one to be the most convenient. Again, delta x is going to be 1 over n, and my xi stars are going to be I over n, just like before. All right, and of course the partitions are going to be I over n, I going from 0 all the way up to n. And here, for this one, of course, I is going to start at 1 and go all the way to n. All right, so there is a slight difference there between partitions and representative points. Okay, now we just have to construct it. We know that the general form of an approximate Riemann sum is going to be f at xi star times delta xi. Now we can just plug in our result from before. So now we have to actually ask, what is f of xi? Well, we know it's, I'll write it here just again for everybody. So now what we're going to do is we're going to take the cube of our I over n and subtract it from x again, which in this case is going to be evaluated at I over n to the first power. Right, so that's the function. And then we multiply it by the delta x's, which are going to be 1 over n. Okay, right, to see if we can move this calculation along, let's do a little simplification of the sum. And note that we have now an I cubed up there over n to the fourth power minus I to the first power all over n to the second power. And those powers are that way because, of course, I'm going to distribute in to both of those terms the delta x term. All right, it's probably worthwhile to put those equal sign or that parenthesis there just to keep our work straight. I'm going to go down to the next line now. And what I'm really going to do now is use the summation trick that we've learned, which is if you have a sum that has two terms, we can break it up into two smaller, simpler objects to deal with. And then, of course, I can factor out the n to the fourth power there. Okay, very nice. And now minus 1 over n squared of the sum I equals 1 up to n of sum of consecutive integers. Okay, from here, now of course I know that I have a 1 over n to the fourth, and I can replace that. This object right here, of course, is going to be, see above, we just found out what that is, and that's going to be the n times n plus 1 all over 2 quantity squared. And now we have this 1 over n squared times n plus 1 over 2. All right. So here is our quantity. I think we're going to need to do a little bit more work to simplify it up a little bit here. And the thing where I'm going to need to do some more work on it is foiling out this quantity squared bit here. So I see this square is going to come down into that denominator, and it's going to give me a 4. So in fact, I can deal with that by having the n to the fourth, and I'll just times it by 4. And then I'm going to have a n squared plus n quantity squared. And now in the next term, I'm just going to have that n squared plus 1 all over n squared times 2. All right, I'm going to move that over now. And actually, let's write just over here in this little corner. I want to now multiply that out. That gives me an n squared plus n times n squared plus n. All right, so we can calculate that to be n to the fourth plus n cubed plus n cubed plus n squared. I can rewrite that as n to the fourth plus 2n cubed plus n squared. All right, so that's now what I can put in its place from before. Now to put this all together, we have n to the fourth plus 2n cubed plus n squared all over n to the fourth times 4 minus n squared plus n all over 2n. All right, at this point, what I might want to do is actually just erase those equal signs, because I've just written this down. that is the value of this approximate sum. If you plugged in a value of n, you would get an estimate for the area under the curve. But now what I want to do is actually take the limit as n goes to infinity, and we should be able to get a nice answer from it. And just like before, we note that it's really just the leading power terms that matter, the coefficients top and bottom. And the same here, the leading, that should be a n squared in the bottom there. Okay, the coefficients on those terms are the only ones that matter. All the other ones in the limit will be nothing. So what we can see here clearly, it's going to be 1/4 minus 1/2, otherwise known as -1/4. Just like we had suggested, the area under the curve will be negative, and we see that now clearly it's -1/4. I think guessing this value would have been not something I could have been able to do just right off the top of my head, but we did predict that it was going to be negative, and it certainly is. And we can see now that these Riemann sum calculations really do work. They do give you a limiting value, and we can safely say now that that truly is what the area under that curve is. So hopefully these two Riemann sum ways of doing integrals have been helpful. I'll see you in the next video where we're going to learn more properties of the integral, where we're no longer going to do these tough summation calculations, but we're going to actually look at ways to simplify our work by looking at properties of what integrals are more generally. Thank you very much.